Welcome. The title of today's notes is Permutations, and permutations for us will represent a very specific variation of the counting principle. So our job today is to kind of see what criteria need to be met in order to call it a permutations, and then from there, what type of mathematics is involved in coming up with the correct answer. So we'll go ahead and take a look. Obviously, we'll explore some ideas together and then do a couple examples sort of at the bottom there to back it up. So I have an example one just to kind of review a couple things and get us thinking in the right direction, hopefully. And it says a baseball team consists of 9 players. How many ways can the first 4 positions in the batting order be arranged? All right, that sounds great. So in this case, here's what I'm going to ask us to do. Let's start out with our little slot diagram that we came up with on the previous notes worksheet. And so this would be how many possibilities are there for the first batter? And obviously, in this case, the baseball team consists of 9 players, so there are 9 possibilities for whoever bats first. Okay, and then my second task at hand is to see how many possibilities there are for who bats second. And so what I would do here is figure out how many different players are left, and if somebody batted first, well, then that means there are only 8 players left to bat second. And then working our way on down here, of course, we'll see third. How many possibilities are there for a third batter? It looks like 7. And last but not least, everybody, it looks like for fourth, there are 6 players left to bat fourth. And so what we would do here is certainly just multiply the number of possibilities for each task together. So there's our counting principle in action. And I'll go ahead and just bring the calculator up. I'll be using this a lot over the course of this lesson. So just nice and straightforward there. 9 times 8 times 7 times 6. And we end up getting 3,024. Perfect. So there are 3,024 different possibilities for 9 players batting in the first 4 positions. Now, just if you kind of stare at our answer here, and we'll go through this process, of course, but if you sort of stare at our answer, doesn't it have kind of the feel of a factorial? Just kind of 9 times 8 times 7 times 6. It looks like it's an abridged factorial, doesn't it? We're missing the 5, 4, 3, 2, 1 on the end. Keep that in mind as we go through. All right, well, just as it so happens, example 1 is a prototypical example of a permutation. And so on your paper, it says definition of a permutation. You'll hear these 2 buzzwords come up a lot with permutations. How many orders or how many arrangements? And in fact, if you kind of see in example 1, it did talk about arranged. So that is definitely sort of a giveaway that we can use a permutation here. So it's an ordered arrangement of distinct objects. Distinct means different. In this case, different players. There was one player, and then a different player, and then a different player, and then a different player. So distinct objects. So ordered arrangement of distinct objects and without repetition. That's the other key to this, without repetition. So for example, as soon as you see in a particular counting problem that repetition is allowed, then permutations, it's not a candidate for using permutations, just FYI on that. Okay, so ordered arrangement, and that's exactly what here. We're ordering 4 players out of the 9. All those players are different from one another, and I can't repeat the player. Whoever bats first cannot also bat second. Okay, perfect. So what I figured we would do is use that definition now to get a little investigation going. And we'll do 2-letter permutations of A, B, C, and D. So 4 letters. The order does matter in which we place these 2 out of the 4 letters. So I guess the way we want to say this, to start it out here, A and then B would be 1 2-letter permutation from these 4 letters right there. Notice it is an arrangement, first of all, A and then B. Distinct objects, obviously 2 different letters. And no repetition. I can't do AA. So A and then B. That would be 1 2-letter permutation. And let's just kind of keep it moving along here. A and then C would be another permutation. A and then D would be another permutation. Now here's the one that comes up. As we look at this, this is actually a separate permutation from this one over here. A and then B is obviously different than B and then A. Arrangement, the order does matter in which they're placed, so we count this as one, and we also count that as one. Okay, so B and A would work, B and then C would work, B and then D would work. Kind of a first and then a second. And then you can start to see if you want to go ahead and work ahead of me on this, that's perfectly fine. But I'm getting a C and then A, that would be nice. C and B, C and D. Notice no repetition, I can't go C, C on that. And then last, as you can see, D and then A, D and then B, and then D and then C. And notice these are two different permutations right here. C and then D is different than D then C. I don't think I can come up with any more there. So let's go ahead and just put, how many are there? It looks like 12. Now one thing to kind of note with this, and I almost have it as in quotes on my paper just as said it before, let's be very clear about this because we're going to contrast this with an upcoming lesson, but AB is different than BA. The order does matter, and they are obviously placed in different orders, so they are different permutations. So AB is different than BA. Wonderful. So we're going to talk about some phrasing here. We'll talk about some notation that goes with this, and then a formula as well. And then we'll go back and kind of relate it to that example one that you see at the top of your page. All right, so I hope everyone's okay with what we see right here. And by the way, this would be 4 letters arranged 2 at a time. And so that kind of leads into our phrasing that you see on your paper. What we're going to do is start out with a certain number of objects, n objects, distinct in nature. For the investigation, it was 4 distinct letters. For the example one, it was 9 distinct players. So we start with a group of objects, for lack of a better description there, and we are going to arrange those a certain number at a time. So I'm going to write R at a time. So if you kind of look at this piece, just again, the phrasing that I would use for this, 4 letters arranged 2 at a time. Here, everybody, 9 players arranged 4 at a time. And so that's how we're going to say it. We're going to have our n value. That's the set that we start with. And the R value, what we take from that set. A subset, if you would. All right, so some notation that you're going to see and a formula that goes with this. So for the first time, we see our N and R with P together. So this is our first original set. The P tells us it's permutations, and the R tells us how many we're going to arrange at a time. And this formula that works out really nicely, I didn't leave a ton of room here, so I'll see what I can do. But it deals with factorials, and so it's based on n factorial over, and sorry again, just write it as a fraction if you get a chance, over n minus r factorial. And so we'll play that out a little bit here, and then I'll show it to you on the calculator as well, and we kind of see how this works out. But you'll see that this formula makes perfect sense with what we developed up above in example 1, and then also with this investigation right in here. So what do you say we just take a minute or two and make a couple connections with this formula up here, starting with a certain set of objects and arranging a subset of them at a time. So here's how I would kind of play this out, everybody, just looking at number 1, is I had 9 players, and I'm going to arrange 4 of them at a time. And watch how this calculation mirrors exactly what we came up with when we thought of it in terms of the counting principle. And as I said, this is just a very specific variation of the counting principle. So if I think about this, this would be 9 factorial on top, and this would be 9 minus 4 factorial down on the bottom. And let's see what that would mean mathematically and why we get exactly what we would think would happen. So 9 factorial, of course, everyone, is this. 9 times 8 times 7 times 6, right down the line. Everyone, if you would, put that on your paper. There's your 9 factorial. Now, the 9 minus 4 is obviously 5. 5 factorial is going to be 5 times 4 times 3 times 2 times 1. Now as you can see, numerator and denominator here, some good things are going to happen. Common factors, everyone, cancel. And look at that 9p4, what operation that really does with this calculation right here. Doesn't it do exactly what we came up with? Our slot diagram, 9 times 8 times 7 times 6, sort of the abridged factorial. So that's what it does. It basically cuts off the factorial at the appropriate spot. Everyone okay with that piece? Okay. So let's take a look at this one. And again, just from a counting principle perspective, if I asked you to arrange 2 out of these 4 letters, you would probably make a little slot diagram and you'd say, all right, well, there are 4 possibilities for the first letter. And then because I can't repeat, there are only 3 possibilities for the second letter. And 4 times 3, of course, is 12. So you would think about it from that counting principle perspective and probably do exactly that. All right, well, let's go ahead and see it from the formulas perspective. And then we'll go ahead and pick up the calculator and let it do a couple things before doing our examples. So this would be a set of 4 elements arranged 2 at a time. And so this would be 4 factorial over 4 minus 2 factorial. And based on that, 4 factorial is 4 times 3 times 2 times 1. 4 minus 2 is 2. Factorial is 2 times 1. Cancel, cancel. And as you can see, 4p2 really just means 4 times 3. And there's your counting principle right there. So you can see it's a nice look at the counting principle. Works great. Now, let's get the calculator to give us a little help with some of this. So rather than kind of doing the expansion with the factorials or anything like that, we're going to go ahead and just sort of type in. So I'll work backwards here. Everyone, if you get a chance, grab your calculator and hit 4. Go under Math, into that PRB, and there it is. There's your NPR for permutations. And so I'm going to go NPR and 4P2. And there it is. There's your 12. Remember the baseball problem? Let's see that in terms of a permutation. That would be 9 elements, and I'm going to arrange 4 of them in order. And 9p4, as you can see, is 3024. Okay, so when we do this, of course, this is how we're going to play it out. But I do need you to see, of course, where that formula came from and where those numbers, where our answers are coming from. Perfect. Let's move on. So let's just run 4 good problems. Nice and straightforward here. So example 2. It says, in how many ways can 15 books be arranged on a shelf? So picture yourself, if you would. You have 15 books lying at your side, and you're standing in front of a bookshelf. It can fit all 15. In how many ways can we arrange those 15 books on that shelf in front of you? Well, this again, you can think of from a counting principle perspective, but basically this is a great candidate for permutations. I have a set of 15 books, and I'm going to arrange them. They are distinct books, and obviously can't repeat. A book that is set in the first slot cannot be set in a different slot. So distinct objects, no repetition, and so it should be just 15p15. And so let's bring the calculator up. Watch this number here, by the way. And when I do 15p15, let's go ahead and do that together. I grab that, move it on over to PRB when you get a chance. And 15p15, huge, huge number. So this would be moving the decimal point 12 places to the right, And so you get what you can see is a very large number. I get about 1.308 times 10 to the 12th. So we're talking about, oh my goodness. So it looks like about 1.3 trillion from my calculation there. Pretty incredible. Now just one thing to note on this piece, if I was to go ahead and use the formula itself, this would be 15 factorial over 15 minus 15 factorial. And you can see basically you're going to get 15 factorial on top over 0 factorial, and you get this number over 1. And so what happens, it ends up being just 15 factorial. So we can see sort of another context. I've already kind of shown you that 0 factorial is defined as 1, and you see obviously that has to be a necessity here in order for this to work. So that 0 factorial just puts it over 1 basically. All right, perfect. Let's go ahead and do example 3. So now same deal. Oh, no, I'm sorry, there's one thing to do first. It says if you were to be able to complete one permutation every minute, how long would it take you to arrange the 15 books on the shelf? I guess this problem is just to give us a context of how large that number is. And so this is the number of permutations. So what if I could do 1 per minute? So let's see this for just a second here. So this is how many minutes it would take if I was to do 1 permutation every minute. That's interesting. All right, and let's see. Let's put this in years. Why not? So when you get an opportunity, let's do a little dimensional analysis on this. Excuse me. Let me say that again. Dimensional analysis on this. So let's go for it. I've got an hour in 60 minutes. So dividing by 60 would give me the number of hours. Let's keep going. And so how about a day? 24 hours. All right, dividing by another 24 would give me the number of days it would take. And let's see, let's go years on this. How about we do 365 and a quarter? Sorry about that. Let's get that together. So 365 and a quarter. Change the days, and that would put me in years. So divide by 60, divide by 24, divide by 365 and a quarter, and I actually have this one on my paper. So even if you did all that, you're able to do 1 permutation every single minute. This is how long it would take. This is the number of years that would be in play. Oh my goodness. So you could see how dramatically large, just something pretty simple like 15 factorial or a permutation 15p15, how incredibly large that is. Random, but interesting. All right, let's do 4. Example 4 says, in how many ways can 6 of those 15 books be arranged? All right, so one more time, just picture yourself. You have 15 books at your side there, but you have a smaller shelf in front of you, and only 6 can fit on that shelf. So we start with a set of 15, and we are going to arrange those distinct objects, no repetition, but we're only going to arrange 6 of them at a time. And so it would be 15p6. I'll bring my calculator up. This one should be a little more manageable. But let's see. Again, permutations really brings up some incredibly large numbers. So 15p6, and just by that, that would be 15 possibilities in the first selection, 14 possibilities in the second, and I'm getting about 3,603,600 ways that can happen. That's how many different arrangements you can make with just having 15 books and arranging 6 on the shelf. So you can see just the dramatically large numbers there. Perfect. Hey guys, let's do the last one here. And I actually sort of remember this one. This one's pretty fascinating actually. So here's the deal with this. In the Kentucky Derby in the year 2005, you can buy what is called a superfecta ticket, and it's common to buy a $1 superfecta ticket. And I'll explain that in just a sec. But $1 superfecta ticket, if you got it right, paid out $864,253.50. Let's put a little decimal right there, 50 cents on that. Now the superfecta occurs when you pick the first 4 horses in order. So you know who wins, that's first place. You know who placed, that's second place. You know who showed, that's third place. And then you also pick the 4th place position. And so it says if there are 20 horses, and there are 20 horses, by the way, in the Kentucky Derby, so if there are 20 horses entered in the race, how many different superfecta tickets are possible? And so this happens to be, when we look at it, a permutations problem, because I have a set of 20 horses, and we're looking for how many different ways you can arrange 4 of them at a time. First place, second place, third place, and fourth place. An arrangement of 4 horses out of the set of 20. And so it's 20p4. Now watch what's kind of fascinating about this answer, and think about what it was worth, and we'll see it. So 20 horses. Out of those 20 horses, there's going to be a first place, a second place, a third place, and a fourth place. And so I would arrange 4 of those 20 horses, and that would be our 20p4. And I hit that, and I get this. So as a matter of fact, this would be 116,280. So if you sort of think about it from a ticket perspective, that's how many superfecta tickets were possible. Now what's so incredible about this situation here? This is how many tickets there were. This is the payout for $1 if you got the correct one. So what would it have been worth doing during this particular race? Well, as you can see, if you bought 1 of each, you would have only had to pay $116,000, roughly, and you would have gotten 1 of each, so you would have been guaranteed the winner, and the payout was over $800,000. Quite a profit there. And the question, of course, is why? Why did it work out there? And here actually is the reason, is that it just so happened in this particular year, during 2005, the horses that did really well, the ones that placed first, second, third, and fourth, were actually long shots to be successful during this race. So every horse coming in has a certain odds, essentially, as to their prediction on how well they're going to do. But it just so happened the ones who did well were not expected to do well here. And as a matter of fact, I kind of looked this up briefly. The winner, the first place, was a 50-to-1 shot. So a fairly long shot to win the race. And so what that did is it just made that ticket worth more than some of the other ones. And then in conjunction with that, the horse that placed, that was coming in second, was 72-to-1 in terms of being able to place that high. The third place, I think that's what's called when you show. So third place was one of the better horses, at least predicted to be better. So the odds of showing was 4.5-to-1. Not too bad there. And in the fourth place horse, the odds were 30-to-1. Again, pretty much a long shot there. So you could see 3 out of the 4 that made the superfecta ticket up, were long shots to be so successful. And that's why that particular ticket was worth so much. Certain tickets are worth more than others depending on these odds. Now, I would venture to guess that most years the payout for $1 superfecta ticket is going to be lower than this amount right here, obviously, to avoid somebody buying all of them and automatically making a profit. So, pretty fascinating problem, though. I remember when this kind of came out and there was a big hubbub about this. I think a couple people actually did win this. The $1 superfecta over almost $900,000. Okay, so not too bad. Just a nice variation of the counting principle. One more time, that definition. So n distinct objects arranged without repetition. And if that sort of it fits that criteria, it's kind of nice to just use a little NPR on that. Hey, thank you for listening. Try some of these problems out, of course. And if you have questions, don't hesitate to ask.